name's Robert Kennedy, PhD student at Florida Atlantic University in Boca Raton. So I'm real close to the Boca Raton office, the LexisNexis Boca Raton office. My presentation is going to cover two main things. The first being HPCC Systems virtual machines on Hyper-V, as well as expanding HPC Systems deep neural network capabilities, specifically with GPU acceleration. First, I'd like to start with a quick poll. How much experience do you have with deep learning, if any at all? Please answer, and we'll go over this at the end of the presentation. So like I said, this presentation, I'd like to go over my work that was completed over this past summer internship. Really excited to be back for a second year in a row as a summer intern. And a quick shout out to the platform team at Boca for extending me to a desk while I work. Thank you. So the first part of my project, I created a tool that's used to build virtual machine images on various platforms. It's an open source tool. It's called Packer.io. It can be run on Windows, Mac, Linux, OpenBSD, and Solaris. What it does is it will create virtual machine images locally based off of a config file. You can use it to create different images. For instance, a Hyper-V image with HPCC platform fully installed. You can create an AWS image. You can create an Azure image. You can create a VirtualBox image. You can create a Parallels image if you're on a Mac, which would be really great. And there's plenty of other for. Currently, as it stands, there's a Hyper-V, AWS, and VirtualBox runtime. All these images come with the standard HPCC Systems platform, but it's very easy to extend this to install custom programs or tweak the version of your HPCC system that's installed. All you have to do is modify the JSON file. Next, I kind of did a case study of how to use this tool. So I used it to create a sort of custom AWS image. Amazon calls them AMIs. It has HPCC Systems 7.2.14, I believe, installed. And it also has all the requirements installed to utilize an NVIDIA GPU, which will then be used in the second part of my presentation. In the second part of the presentation is going to be a GPU-enabled deep learning bundle. Both the bundle and the Packer script and tool are on GitHub. The links are displayed here. I think the links are in the presentation window as well. So please definitely go take a look at them, comment, use it, let me know how it works. I'd really love to see people use it. So HPCC Systems on Hyper-V. That was the main goal, I guess, for the first part of this. Hyper-V, for those who aren't familiar, is a hypervisor that's used to run a client operating system within Windows 10, similar to VirtualBox, except it comes as part of Windows 10. Unfortunately, VirtualBox and Hyper-V can't run on the same system at the same time, which can be a little problematic. But basically, the Hyper-V images, so you could use a local HPCC node, but running in Hyper-V. And like I said before, this uses a JSON config file, very easily extended, and it's documented in the GitHub repository for easy use. So real quick, why Hyper-V? Well, other than it would be yet another platform supported by HPCC, at least for development environment. This idea was first presented as an internship project proposed by the company. So you guys obviously saw the importance. And secondly, it was originally thought that using Hyper-V would allow the use of GPUs locally. Unfortunately, it turns out that's not exactly possible due to the way Hyper-V works. But for instance, which we'll go over shortly. Even though it's not compatible with, even though Hyper-V is not compatible with GPUs, I thought it was very important to develop this because Hyper-V is a hypervisor that ships standard with Windows. So you don't have to go out and download a VirtualBox, which is a whole other thing. But also importantly, if you happen to run Docker Desktop on Windows, that actually runs in a Hyper-V VM. So if you're running VirtualBox, you can't run a Docker Desktop. So if you happen to have Docker Desktop as part of your workflow, you can now have on the same machine as part of your workflow. You can now have on the same machine at the same time a local node running in Hyper-V, which I think is great. So I use this tool to create a customized image that's running HPCC and is able to use a GPU for accelerated computation. It supports Python 3.6, CUDA 10.0, TensorFlow 1.14, and PyTorch 1.1. Those are at least the ones I use. Oh, and I think I mentioned the specific version of HPCC I used was 7.2.14. These were deployed and compiled and deployed to both AWS and Azure for testing. I feel that AWS has more cutting-edge hardware options at this point. They have the newer graphics cards if you were to use this for accelerating deep learning. However, as we'll go over in the case study, it's not necessary to have the absolute fastest GPU to realize significant performance increases unless you're at the bleeding edge of deep learning research. Even the cheapest and smallest, the K80, you can realize some very, very significant performance increases. Right, so quick overview on deep learning. This is an increasingly dominant subdomain of machine learning, as I'm sure you know. Deep learning architectures, which are basically artificial neural networks characterized by having both a large breadth and a large depth of layers, so very wide and very deep neural networks. These benefit from training on big data. Unfortunately, the size and complexity of the models combined with the size of the training data makes training these neural network models very computationally expensive. One solution is to accelerate the training procedure using large cluster computers, such as a standard HPCC system, but that has its own challenges. In contrast to this, where basically you just add more CPUs to the problem, another solution is to offload the heavy computations of the neural network training process itself directly onto a GPU. This technique can be, if you ever played around with it, it's significantly faster than on even multiple CPUs. And this is even more so for convolutional neural network. So currently HPCC had some common machine learning algorithms and some distributed deep learning runtimes, but they were all limited to CPU for the computations. So that was the main goal for this part, was to leverage a GPU with HPCC, which is, to my knowledge, I think might be the first to do that, at least specifically with neural networks. So what are we actually calculating? So real quick, this is what a neural network looks like in the lower right. Upper right, this is what a neuron looks like. There's a lot of steps, a lot of mathematical operations that have to occur. So the artificial neuron looks a lot like a biological one. Just like the biological one, it accepts inputs from the previous layers, the previous neurons, with an addition of a weight, with a weight that this weight is what is changed during the neural network training process. And as you can see on the image to the right, you start with your input layer, and then it goes down to the next hidden layer, to the next hidden layer, to finally the output layer. And this is a trivial neural network model. So you can imagine when they get very complex, these weights and the required computations grow really, really quickly. And luckily, GPUs can handle these. So where exactly do the GPUs come into play? Well, during the neural networking process, the main parts, there's the forward pass, where the data is fed into the network from the input side, and an error value is calculated based off the input data, and the loss function for each neuron on each layer, and then it's calculated for the next layer, and it's calculated for the next layer, and it's calculated for the next layer for each piece of data. So if you have a training data set of 60,000 images, which is pretty standard, you have to do this, 60,000 times however many epochs you want to do. So it adds up. Second part is the backward pass. Once you pass through all the data and calculate all the error, you have to then propagate it backwards, and you have to calculate the gradient for each one of those arrows, each one of the connections with respect to the error. And you have to do it backwards for each and every one of these pieces of data. So this is really where the computationally expensive part happens. And I won't go into too much detail here just due to time, but it's basically the gradient descent algorithm is what causes it. Okay, so as you might expect, this is not exactly your average HPCC system. Traditionally, a system would have use a bunch of commodity computers connected via standard network protocols, which can be quick, but with respect to deep learning, this is a very large communication bottleneck, partly due to its iterative nature. So a distributed CPU system might not be the best way to go about solving this problem. Real quick, the paradigm in which the training process happens is called data parallelism. Data parallelism is basically what happens is the data is partitioned across multiple nodes, either GPU or CPUs, and a copy of the neural network model is put onto each one of the nodes. The model is then trained on its local subsection of the data until a certain point, and then everybody stops, all the nodes stops, and then the models are aggregated at certain predefined points to basically have all of your nodes working in unison to create a single neural network model. So you can see this is kind of an image of how it would work. So the parameter server, the green squares would be your CPU, and the blue squares would be your GPUs. The connections between them would be your hardware connections, and then the data shards down at the bottom below the squares would be the localized the GPU memory. All of this is happening basically inside of a single machine, which is in contrast to traditional HPCC systems where it's across multiple machines. So that's a nice takeaway. So with this bundle, you can train neural network models on the GPU. You can also do it on the CPU if you so desire, using data that's stored in HPCC. It's sprayed on HPCC in the standard way. This bundle is brand new, still in its infancy, but you are able to build, train, and use a neural network model by using either ECL only or using ECL and Python. So you'd have to write ECL and Python and ECL together. If you want, is you can have fully customized neural network models to train on data housed on HPCC. You can also make predictions, so you can consume, you can use, you can infer with these neural network models also on a data that's housed on HPCC. So you can kind of, from the whole workflow of designing, testing, training, and using in production, a neural network model can be realized with this bundle, all while using a GPU to accelerate the training process, which can take a long time. Can't really go into too much detail here, but I do want to let you know I will be going into this in much more detail with code examples, output examples, and everything at my Community Day presentation coming up in less than a month. But this is what it would output. So in this task, the model is trained to recognize a handwritten digit. In this case, on the left, it's an 8, obviously, and on the right-hand side, you can see an output in ECL Watch, 10 rows, and it's encoded in what's called one-hot encoding. So what one-hot encoding is in this example, there's 10 digits, 0 through 9. So there's an array of 10 integers, all of which are 0 except for one of them, and it's a 1, and the index of that 1 indicates the class that the neural network model predicted on. So this is how you get your usable, actionable data from the neural network model in HPCC, which is great. So a quick poll before I go into my performance evaluation. Approximately what time frame do you see having the need for deep learning, if at all? And we'll go over this answer at the end. Okay, so quick performance evaluation. I did a case study to measure the performance improvements. I trained 5 identical convolutional neural networks, or CNNs, on the MNIST data set, which is handwritten digits, and I did them 10 times each. I did this on CPU alone, 1, 2, 3, and 4 GPUs to show the difference between using a GPU and not using a GPU, and then showing the increase in performance for each additional GPU. The machine I used was using older K80s, and anything newer would only have bigger performance increases. So this is training a CNN on the MNIST data set between a CPU and a GPU. This was a Xeon CPU, so a pretty decent CPU, I guess, versus a K80 GPU, which is fairly outdated at this point. You can see that the total training time for the CPU took 1,108 seconds, and then on just a single GPU, it took 202 seconds. So it's a 5.4-fold times increase for just using one GPU. And this is on a toy model, on a toy data set. The performance increases are even greater on when you have a bigger model and you have bigger data. So this is kind of like, it only gets better from here. This is a comparison between CPUs and GPUs, but also between the number of GPUs, as well as comparing that to the optimal speedup. So when I say optimal, I mean a linear speedup. So if you use twice the GPUs, it should go twice as fast, which it won't, as we know, because of communication bottlenecks. However, you can see the blue and the green line. The green line is the GPU performance, and the blue one is optimal. You can see that it's very close to optimal as you keep adding GPUs, which basically means there's minimal cost for adding an additional GPU, and you do, in fact, you keep increasing the performance as you keep adding the number of GPUs. They get expensive, though. So in conclusion, I created a tool to create some virtual machine images for Hyper-V, AWS, and Azure VirtualBox, and I demonstrate a good use case of using a customized image. I want a brief overview of the GPU Accelerated Deep Learning Bundle. And again, there will be much more detail presented at the breakout session at Community Day. I think I'm rotation 2, theme 1. So please come see me. Here are some links. The presentation is downloadable, so you can go back and look at this later. And before I conclude, I'd like to ask a third poll question. How important do you think it is for HPCC systems to have deep learning capabilities. So, any questions?
Okay. All right. Thank you, Robert. You know, I think deep learning continues to be a popular topic with our community, so I'm glad that you're able to be here and share your work with us. So we do have some questions coming in from the audience. So while you review and prioritize those, I will go in and share the results from your first poll. And the question you had asked was, how much experience do you have with deep learning? And to me, this is always an interesting question to ask, so we can get an understanding of the background of our audience on who's listening. And lo and behold, 60% said that they have no experience but are very interested in deep learning and learning more. And 20% said that they have experience but not in neural networks. And while the other 10% said that there's no experience and not really applicable to their role, and the other 10 said that they are experienced with deep learning. So an interesting mix, but an astounding 60% with no experience, but very interested. All right, so Robert, are you ready for your first question?
Sure.
Okay. All right, so are there specific GPU requirements? And you had already mentioned the ones manufactured by NVIDIA.
Sure. So as of right now, NVIDIA graphics cards, discrete NVIDIA graphics cards are the only ones supported. You have to have meaning you can't have a GPU on a CPU, which is quite common now. You have to have dedicated graphics cards. And that's kind of mainly because NVIDIA saw the need for this type of, they actually created a whole new API and programming language to access the GPU. They saw the need for that way before everybody else. So their tools that are used are much more robust and pretty much exclusively used, which is kind of amazing.
Yep. Okay, well, thank you for the insight on that one. And your next question, are there any downsides to using a GPU for training a neural network besides hardware costs?
Not really. Obviously the GPUs are expensive, but an older GPU still increases the performance by a huge amount, and they're getting cheaper. You can pick them up used sometimes. But no, there's typically no downside to using GPUs. I guess if you had too small of a graphics card memory and too big of a data set, you'd spend too much time transferring data between disk to graphics card memory. So I guess it would really depend on your specific use case, but typically not really. They're almost always faster.
Okay. All right, well, thank you for providing insight there. All right, so in the interest of time, let's just go over the results from your last two polls. And midway through, you had asked approximately what time frame do you see having the need for deep learning? And 66% said within the next 6 to 12 months, while the rest, the remaining 33%, said they need this immediately, that they're either currently using or about to start. So it's interesting, timely there, I would say. And your final poll was, how important do you think it is for HPCC systems to have deep learning capabilities? And the results show 100% said that they think it's very important. So obviously, based on these results, it seems the community will definitely benefit from your bundle. So thank you so much for contributing that.
Oh, thank you. I'm glad I'm the only one that thinks it's important.
Yeah, absolutely.